formula to calculate, just put it there, and because it's quick, so I will show it here. Okay, so this is not that hard, but the reason I put it here is because you can kind of get yourself familiar with the calculations of like operation of expected value here. Okay, so first you do the distributed rule and to kind of expand it within the bracket here. And then since this is a linear operator, so you can separate into 4 pieces after you expand these two, the multiplications of these two terms, right? And then go to these equations here. Remember that we cannot directly separate these terms, right? And how about the second term? The mu x here is actually a constant. Okay, so that's why we can take it out of it. So that's why I can write it down this way. And for the third term, it's the same reason. The mu y is a constant here, so we can take it out and write it this way. Okay, and then you will realize that, these 3 terms are the same. What's different is the sign in front of it. So these 2 can cancel out, and you rewrite these terms into this way because mu x is the expectations of x, and that's why we can put it this way. Okay, Lenz's Jensen's inequality. This is an inequality that you are going to use a lot in the proof in the econometrics. Okay, And first, let's refresh the memory a little bit. What is the convex function? What is concave functions here? Okay, so for convex functions, that means this. This is the definitions, and this is the concave functions. Okay, and in the operations here, like if we use the how to say that, the expectations operator here, that also fit into this relationship. So this is exactly the Jensen's inequality. Okay, and to show it, so this here has an example to apply the Jensen's inequality here. Okay, right. So look at this theorem 4. This AJ here is actually you can take that as the probability weight. So what is on your right hand side is actually the expectations of the random variable x. You can take it that way, and that is always greater or equals left hand side. And the proof is quite simple. You just take log on the left hand side, and that will become this way. And because loss is concave functions, and apply Jensen's inequality there, then you get the result. And you get this inequality, and then you take exponential on both sides, you will get the result you want. So that is the proof. Okay, so of course, like in the real world, it's quite complicated, and sometimes like one single one single random variable is not enough for us to use, right? To discuss a lot of things here. So that's why we have this multiple random variable as well. Okay, so if we go back to table 1 again, for example, like P of x equals h and y equals to c. What does that mean? So that means when I random draw a person from that population, from that samples, what is the probability of that person has higher wage, like high wage and college degree? Okay, so these tables tell me is 0.19 here. And that is exactly, where is it? Here, that's exactly this probability. So if we take the x as the wage and y equals the education label, and that is the interpretations here. Okay. And of course, like this is a discrete type, we can transfer it into, like kind of translate it into a like random variable. Okay, remember that we have the coin toss example there. Okay, so this is use the table as an example here. So if that person has like earns high wage, then put x equals 1. If low wage, then put it 0. If that person has a college degree, put y equals 1. And if that person doesn't have